example 1 is going to be based on chapter 1. I plan on having 4 problems. Again, it's not sure yet. I plan on having 4 problems. And each problem would be 25 points. Each problem would be 25 points. It depends. You may see slightly different. And each problem will have subproblems. So you will see a problem P1 will have A, B, like that. Okay. So it depends how I divide. So each problem will have some subproblems. From chapter 1, chapter 1, you may expect 1 and half problems. From chapter 1, you may expect 1 and half problems. From chapter 2, it is you may expect approximately 2 and half problems. Yeah? Each problem, for example, problem P1, and then you'll see A, and then you'll write. So you'll write, there will be a problem, and then you will see some empty space. Please pay attention, guys. I'm giving all the hints except the questions. Okay, all the hints I will look except the questions. Make sure you pay attention. Here, because of the space limitation, and I know that if you know the answer, okay, you should be able to fit all your work inside this space. If not, there is a possibility that you will run out of space. What I suggest that you divide the empty space like that. You divide the empty space like that, and then start your solution right from here. Right from here, and then once you run out of space, you go here. And then once you run out of space in second column, you go right here. You see that? And final answer, make sure all the final answers, make them box. Okay? And do not simply write the final answer if you don't. Okay? Do some work as well. In case your final answer is wrong, based on your work, you will get 80% of it. Is that clear? In case your final answer is wrong, you get 80% of your okay. So this is about procedure. Now let's dive into chapter 1. So module 1, signals and amplifiers. This time, I don't plan on having true false type question. It's going to be all numerical problems. All numerical problems. So you can just read this for your knowledge, but I'm not going to ask you what is signals and signal amplification. Forget about this type of question. I'm not going to ask you this type of question. So it's going to be mainly numerical. For example, here, video example 1.1. So I will give you a circuit like this, and I will give you all the values. Okay? I will give you all the values of these resistors. Ryan, are you taking notes? Ryan, are you taking notes? So you don't watch cell phone, as I said that I'm giving all the hints. please pay attention.
Yeah.
You don't need laptop now. You can take notes in your notebook. You don't need laptop, please. So you will see circuit like that, and then I am going to provide all the values in the question. Now, what I would like you to do immediately, what you do immediately, write down these values right here, right on the circuit diagram. Because I will be drawing the circuit, I will not give you values right here. I will give you variables, just like what I did right here. Okay? I will give you variables R1, R2, VS1, VS2, R3. Please, based on the data that are given on top of the problem, immediately write down the values. Okay? That way I know I will know at least you are working on the circuit. So here, find the current in each of the 3 resistors and motors and their common node. Using 2 methods: loop equation, node equation. Okay. So I went through the solution. Even author has provided a video. The way author has provided the solution, my solution is a little bit different, but the end result is the same. End result is the same. So where to get the video? So how many of you have electronic version of the video? Okay, so if you read electronic version, you see this is the video example, and then if you just click here, you can watch the video of one of the authors. And then these exercise problems, you can see the answer. You can see the answer, but you may want to take a look at. You must solve the exercise problems that I listed in my slide. You know, in my slide, you see there are some exercise problems I listed. You must solve those exercise problems. Okay? And the other exercise problems, those are not suggested, but in case you have one short question on those exercises, you may just practice. But emphasis is going to be given to the exercise problems that I listed in my slide. Okay? So keep this in mind. Therefore, you should solve all the exercise problems that I have listed in my slide. Now, this exercise, video example V1.2, for example, or V1. Or example 1.1. What I did, using this convention, example 1.1, VE 1.1, and then exercise 1.1, things like that, and then end of chapter problems. What I did, end of chapter problems, I mean, if you go to end of chapter problems, I'm talking about this problem. So I'm going to say that end of chapter problems, simply 1.4. Simply 1.4, for example. So what you do, you go to our course website on Canvas. you see homework problem set 1? I have posted that, and I also sent an announcement, right? You guys read those announcements, right? I will also send an announcement. Please read my announcement. And here is the homework problem set. See, the due date is October 6th. October 6th. Our exam is on Thursday. Thursday, October 2nd. So even though due date I have posted, I put the due date October 6th. You submit this homework instead of scribing. But this homework problem set that you see here, strongly recommended problems that you should go through. So video examples, I denoted like VE 1.1, 1.2, examples 1. Examples 1.1, 1.3, 1.5, exercise 1.8, 1.9, end of chapter problems 1.6, 1.12. Did you see the convention, guys? How I use? So you have video examples, and you have examples, you have exercises, and you have end of chapter problems. Please organize your preparation accordingly. So I don't have much problems from chapter 1, but chapter 2, you are going to emphasize more. As I said, that it's going to be almost about 2.5 problems from chapter 2. And chapter 1, 1.5 problems. So,
does the book provide solutions to all the homework problems that you posted?
This book provides as an instructor. I have solution to all the problems. Okay, so video examples, you already have the solution. Examples, you have the solution from the book. Okay, exercise, just the answer, but students don't get the solution. But end of chapter problems, there are some restrictions that I will not be able to post the solution. End of chapter problems. Okay, so but this end of chapter problems that I listed, those are very, very close, very, very related to the examples that I went through class. Okay, as you see, I did not list all the end of chapter problems, just very, very few. So 1.12, 1.16, 1.1, 2, 3, 4, 5, 6, 7. Here you have 6. So only 30 end of chapter problems that I have listed. Okay. So please do exercise again and again, and please don't simply skim over the solution, skim over the examples. Even though author has provided the solution, okay, and I gave you the solution, we went through solution of some examples. Take a piece of paper and draw the circuit, solve. Okay, write down. If you skim, electrical engineering doesn't work like that. If you don't do, you forget, and you will not be able to answer in the exam. Trust me. Okay, I was also a student, the way I studied. Frequency spectrum signals here mostly focus on here. This exercise 1.7, 1.8. And then we have A to D, D to A. Solve the examples that utilize this quantization, voltage quantization size, and decimal number. Okay. So this is another exercise, and this exercise I went through this exercise in class. If you missed some of the solutions, you may want to cooperate with your peers. Okay, get the solution and practice. If you missed some solutions, and please do not keep any questions empty. You have the formula sheet, at least write down the formulas that are related to that question. You don't get zero for that. Here, the other thing, the most important examples that you should see is related to this amplifier model. And this amplifier model, we went through this amplifier model in class, which is this one. Right? We went through this example. It is example 1.3. Because I have redrawn this circuit, that's why I said that it's adapted. And I modified some question as well. And we went through this solution in class. Those you missed, it should you take the solution from your peers. So this is the most important example that you should focus on. Next. Exercise 2.2, 2.3, make sure you solve this. And inverting operational amplifier. You may expect to derive an expression like this. Okay, so here you have simple circuit, only one resistor. Let's say you have another resistor in parallel. Okay, you have another resistor in parallel. Let's say I may give you another resistor in parallel right here. Okay, so based on this resistor, let's say you call this R1, R2, this is R2. Based on this configuration, I may ask you what is the voltage gain. What is the voltage gain? The voltage gain is going to be very different. Okay, the expression. So you come up with that expression, and then in the problem itself, I say that R1 equals 10K, R2 equals 5K, and R3 equals 1K. What is the voltage gain? Clear? So then you will see a numerical value, you will see derivation expression for the voltage gain followed by a numerical value. Now, keep this in mind that I have like problem 1A, 1B, okay? If 1A is, 1B is wrong, given the fact, no, let's put it this way. Let's say you have problem A, problem B, okay? And problem A, you have certain expression, and problem B, you evaluated that numerical value based on that expression, okay? Now, if problem B, part B is right based on the wrong answer that you have, so you get the full points for part B. You get points deducted only for part A. Do you see my point? Okay. So I will grade accordingly. So for every effort you will be rewarded. Only rewarded. Only thing is that this do not give any question blank. You do not need to write much explanation. You can just write main equation. So I know the explanation. So you may want to just write the main explanation, and in case you want to write down one sentence, be very, very tricky. this example is very, very important, guys. Very important, this example. So make sure to go through this example, solve this example at least 2 times. See how I have annotated all the currents and voltages. Design consideration, I also went through this and weighted summary. Here I may give you one or I may give you 2 to 3 registers here. So you have here how many inputs you have? So you have V1 plus V2 plus here, and here will be weighted by some coefficients. So it's going to be Rn over R1, some coefficients, okay? So now you have all of this up to, let's say, R1, R2, maximum R4. Maximum you can get R4 RF over R4 here you have. So I may give some values to RF and R1. You just need to find what is the output. This is weighted summer, and this weighted summer, there is an exercise in the list of homework problems. And in addition, I put these 2 exercises. Okay. I'll be in my office tomorrow. Let me see the calendar, because usually my office hours Monday and Tuesday from 11:30 to 12:30. Tomorrow, tomorrow I can have my office hours as well, from 11:30 to 12:30. So if you have any question, come to my office. Okay? And I am not going to answer any exam related question via email, particularly to one student. Okay? So if I answer that, if I think that I should answer your email, I'm going to answer that email to everyone as an announcement. Okay? Just to be fair. Non-inverting operational amplifier, this is also important. We went through the derivation, so this is the voltage gain. So we have GV 1 plus R2 over R1. VI, and this is V0. Okay. Now, don't think that I will give you a problem very straightforward, just like this. So you may expect 1 or 2 registers in parallel, for example, here. Okay, I may add 1 more resistor, okay? A resistor network, and you may have another, let's say, source. I can transfer source right here, and then you may expect a voltage divider right here. Okay, so this source could be right here, and here you have R3. This is R4. Now I may connect this output to this input. Okay, so like that, what you need to do, you will need to apply the voltage divider and find the voltage across this R4. So as you see that V4, which is the voltage across R4, is going to be R4 over R3 plus 4 times Vi. Now you can think of this Vi as V4 right here. So you will see this expression is a little bit different. So you will see a different expression, and you will have different numerical values. If I give you values of R1, R2, R3, R4, you will see different numerical values. Voltage follower, you may expect a very short question, because voltage follower is coming from this circuit, where you just replace, you just remove this R1 and replace this R2 with a piece of wire. Okay? Okay, difference amplifiers, common mode rejection ratio. You may expect one problem based on difference amplifier. You may expect one problem, full problem based on difference amplifier. Just write down a little note that I said, okay, so that you know what to emphasize, okay? So you may expect one full problem on difference amplifier. You can directly bring this condition in your formula sheet, proper differential operation, or you can directly bring you can bring this condition in your formula sheet, and also the derivation, you know how you do the derivation. So make sure you see how we did this part, because I'm going to dig into it. So go through this derivation, and then you know finally you will need to apply this formula. Okay? Finally you will need to apply this formula. All right. Instrumentation amplifier. Simple difference amplifier has some issues with common mode signals. Some noise could be amplified as well. But these common mode signals can be removed using this modified version of difference amplifier, where you have another stage of amplifier right here. So this is called instrumentation amplifier, and this example, author has provided a nice solution. I'm not going to write down the detailed solution here. So what you see, you go to the textbook. Example 2.3 here, I'm very impressed. the solution. Here, author has nicely drew all the steps, figures of all the steps nicely. These are just numerical calculation from the formula of difference amplifier. Please make sure, it's not that big of a solution. Make sure you go through this example. And slightly modified version of this example is one from end of chapter 12. Okay, so solve that end of chapter problems. Open integrator. This example, we went through this example in our previous class. So, you guys had the derivation, right? So I said that I'm just going to go through the numerical portion today, and the derivation portion, I did that in my last class, right? So I'm just going to go through the derivation portion today, and then I will just follow. Here, derive, consider the circuit shown in figure below. This is the input. We have resistance R1, we have capacitor, we have resistor, and then we have output. So these two, we replaced it with simply C2, and we have Z1 equals simply R1, and Z2 is simply R2 parallel 1 over SC2. So which is basically R2 times 1 over SC2 over R2 plus 1 over SC2. So here we have R2 over 1 plus S R2 C2. So this is the Z2, impedance Z2. This is impedance Z2, this is Z1. And then what we did, we found just going to directly write down the expression that we found already. So we found transfer function G of S, which is V out of S over V I of S. R2 over R1 over 1 plus S C2. So this is the transfer function that we found, and S is the complex frequency. For sinusoidal input, S we substitute j omega equals j 2 pi r. Omega equals 2 pi r. We simply substitute S equals j omega, omega equals 2 pi r. We write this as H of F, which is negative R2 over R1 over 1 plus J 2 pi F R2C. If I ask you what is the DC gain, so here, find the DC gain and 3 dB frequency. DC gain is called DC gain, which means that the frequency at DC, what's the frequency at DC? Zero. So DC gain, which means that you evaluate H of F at F equals 0, which is same as you evaluate G of S with S equals 0. Okay? So which is nothing, but if you substitute S equals 0, it is simply negative R2 over R1. Simply inverting of them. At 3 dB frequency, so if you have frequency, if you have G of S, which is negative R2 over R1, you can write it like 1 plus tau S. 1 plus tau S. Okay? Now, tau here is R2C. Tau here is R2C2, as you can see, tau S, which means R2C2. This tau is called time constant. Is called time constant. This tau is called time constant, and useful for transient analysis. Transient analysis, what does that mean? By looking at the time constant, you see, R2 times C2. So R2 is in ohm. Please pay attention to the unit. If R2 is in ohm and C2 is in farad, capacitor unit is in farad. If you multiply, you get the unit in seconds. Okay? You get the unit in seconds. RC time constant, you get the unit in second. What does that mean, this time constant? What does that mean? How fast the system will respond. Okay? How fast you get the output. How fast the system will respond. That is the main point here. So this time constant, you can use it for analyzing transient response. Now 3 dB frequency, what it means, 3 dB frequency, because you get the frequency. 3 dB frequency, which means that your magnitude, H of F, you get the magnitude in dB is going to be negative 3 dB. So if you take the magnitude, you get negative 3 dB. At what frequency you get the magnitude negative 3 dB? Okay? At what frequency you get the magnitude negative 3 dB? That is called the 3 dB frequency. And this 3 dB frequency is actually, this F is actually 1 over 3 dB frequency angular frequency. 3 dB frequency, omega, it's angular frequency. Angular frequency, omega is simply 1 over tau, which is 1 over R2C2. And this 1 over R2C2 is simply the coefficient of S. R2C2 is simply coefficient of S. And 1 over R2C2, you get the frequency which is in radians per second. And you get 3 dB frequency, you can write F 3 dB. In other words, you can, we'll also denote it with F naught, which is 1 over F naught equals omega naught over 2 pi. So this is in Hertz. So make sure you know exactly what you are trying to find. It could be angular frequency, which is radians per second. It could be physical frequency, which is in Hertz. The final question here. Okay. Design the circuit to obtain DC gain. I want the DC gain to be 40 dB. A 3 dB frequency of 1 kilohertz. So 3 dB frequency should be 1 kilohertz. So design the circuit so that DC gain is 40 dB and 3 dB frequency is 1 kilohertz. Input resistance is 1 kilo. At what frequency does the magnitude transmission become unity? What is the phase angle at this frequency? So here, I'm just going to write down this is you all will know. Now you have DC gain. We want DC gain 40 dB. Okay? Which is basically 20 log 10 h of f magnitude should be 40 dB. So we want h of f magnitude, you can find, you see that this is, oh, by the way, h of f is what? V out of f over V I of f, right? Right? Output over input as a function of frequency, and the unit is volt over volt, because this voltage, output voltage is going to be volt and input voltage is going to be volt. So you have one, okay, can you put it in your calculator? I know the answer, I just want you to find it. Can you put it in your calculator? What is the voltage gain here at this frequency? So DC gain will be 40 dB. DC gain is 40 dB. When I say DC gain, what is the frequency? 0. At 0 frequency, you get, I want a 40 gain, 40 dB gain. So at 0 frequency, output voltage over input voltage is going to be 40 dB. What is the DC gain? Volt over volt. So it is going to be 40 divided by 20. What? So it is going to be 40 divided by 20. No. Log 10. 40 divided by 20 is 2, right? So now what is h of f?
It's the expression minus R2 over R1.
Yeah, but I want to design that, because DC gain is 40 dB. Previously, DC gain we found the expression, but here in the example it says that we want to design the circuit to obtain DC gain of 40 dB.
Well, you just make the ratio,
Exactly. So 1K, I will get there. So we want DC gain to be 40. So what is the voltage gain here? So 10 to the log 10 base 10 H of F is 2. What is H of F? 10 to the 2, right? It's going to be 100 volts. So we want the gain to be 100 volt over volt, which is same as 40 dB. Okay. Now we want to, as Robert said, that we want to select R2 over R1. We want to find it 100. So R1 is given 1K, 1 kilo. So therefore clearly R2 is going to be 100. So if you chose R2 to be 100, R1 to be 1K, you get DC gain of 40 dB. Now, if you get 3 dB frequency, 3 dB frequency F0 is going to be 1 kilohertz. So we know that it is omega naught equals 2 pi F0 equals 1 over R2 C2. Okay, we want F0 to be 1 kilohertz. So R2 is already 100 ohm. So you can find C2 is, author has written the values directly. I'm just giving you from where they come. So 1 over 2 pi R2. How much is it, guys? So C2 equals 2 pi R2 F0. So can you calculate it for me, guys? So 2 pi R2 is 100 times 10 to the 3, and this is 1K, which is 10 to the 3. How much is it? How much? How much is it?
1.59 nanofarad.
1.59 nanofarad. Very good. Again, please don't get confused. This nano is 10 to the negative 9, so which means that 1.59 times 10 to the negative 9. What is the unit now? If I write it like that,
which is farad.
it's just farad. Very good. Okay. All right. So you get the idea. That's how we design. So we design C2. We have R2, we have R1. So we have all the components of the circuit. You see that? Now I want to have 15 more minutes. Please go through example 2.6. Please go to example 2.6. Okay, don't think that from examples, let's say examples, those examples are quite big. Don't think that I may give all the sub-problems from the example. So I will extract some parts of that example. We are limited in time as well, right? So you have to make sure that you will be able to, so make sure you know how to manipulate the different parts of the problem. So differentiator, I said that, please go through this section at home. This section is very similar to the integrator. Now what I'm going to do, rail to rail voltage you already know from the lab. So what I'm going to do, one more topic here is slow rate. And again, I'm not going to ask you what is a slow rate, you just need to know what it is, but you may expect some numerical problems. Slow rate is basically defined mathematically as time derivative of the output. Okay. Once you apply input to the op-amp, okay? Once you apply input to the op-amp, output, drastically you don't get it inverted, or you don't get according to the mathematical expression, okay? Output will take some time. Output will take some time. So that's why you said that, okay, so you have this input here, and this is unity gain. Output, if this is unity gain, output you are expecting just like that idea. But practically, when you implement using an op-amp and implement this unity gain op-amp, you see output will look like this. Okay? So which means output is limited. Output speed is limited. It takes some time. So that's why you see that there is a limitation. So instead of the output which is shown as such, you get output slanted. It's because of the slow rate. And this slow rate you will see in the manufacturer's data sheet. This slow rate, you can actually see the manufacturer's data sheet. And that slow rate says that how fast your op-amp will respond. Manufacturer will put that slow rate right in the data sheet. And our LMC 6482 also has a slow rate. Okay? So make sure you understand that. I'm not going to read my slide here. So there is there are some examples. You may want to you go through those examples. Those slow rate related examples, I have it in the exercise problem. The other topic is active filter. Active filter, you design filters using op-amp. So this is the frequency transfer function, and this section I did not take it from the book. Okay, it's my own note. So this section, just limit this section from my notes, and you see bottle filter. You see that here the gain is this is the DC gain. H0 is the DC gain, and F is the frequency. F is the 3 dB counter frequency, and is the order of the filter. And is the order of the filter. And I plotted this transfer function, this gain, as a function of frequency, right here. As you see, as you increase N, do you see this low pass filter passing the low frequency components and actually getting rid of high frequency components. Okay. Now, equal component silent K low pass active filter. We already know what is this one. This is an op-amp, and we are applying input to the inverting. Here we have second order active low pass filter. We have a feedback register network. We have this gain, and experimentally it is designed, experimentally. So I took this from another book, experimentally it is designed, how much is the value of K? Yes.
What does the bent line on the capacitor mean? 'Cause there's usually two straight lines. What does the bent line mean?
Okay, so this bent line means it's polarized capacitor, it has a polarity. Positive here, negative, positive here, negative. These are polarized capacitors, very good. And the capacitor that you used in the lab, guys, in 221 you should have got some capacitors as well. The capacitors that you see, can anyone tell me what are those capacitors? The name? That capacitors that do not have any polarity. We have this in the lab, and most of the time we use those capacitors. Those are called ceramic capacitors. Ceramic capacitors. And ceramic capacitors, as Robert mentioned, that we put capacitors into like that, which means it doesn't matter which way you put, okay? But we deal with the ceramic capacitors, keeping in mind that, you know, even if you mess up, positive, negative, it doesn't matter. But polarized capacitor, you have to be careful. You have to know, otherwise you may burn your hand. So you have to know which one is positive, which one is negative, polarized capacitor. So make sure you pay attention to that. So we have this K value in the resistor network, this K value, the value of this resistor is going to be K minus 1 times RF. So you choose certain value of RF, and this resistor value is going to be K minus 1 times RF. And this K values, depending on the order. So here we said that, you know, first order, second order, third order. Depending on the order, you get the K values like that. So fourth order means it's a second order here because you have two energy storage elements. If you have fourth order, which means that you will have this copy right here. So this is a fourth order filter. Now I have one example here. These are the fourth order low pass button filter having cutoff frequency of 100 Hz, which means that 3 dB frequency or corner frequency. F naught equals 100 Hz. Now, how to design, how to come up with resistances R1, R2, C1, C2, then R3, this is R4, R3 equals, it was RF, and K1, this is the first stage, and K2, because it's the fourth order filter, so you'll have two K values. So K1 equals 1.152, K2 equals 2.235. These two values, I took it from this table. Okay? So if we have an example like that, you may want to bring this table right in your formulation. Okay? So just to be on the safe side, in case we have a problem like that, bring this table right in your formulation. Okay? Clear? So bring this table, and we chose K1 1.152, K2 2.235, and how I came up with all these capacitors, we already know all the derivations, all the equations. Okay, what I did, I actually typed the solution here. So you have the complete solution here. Okay, because we don't have this in the book, we have complete solution. How to come up with R1, C1, R2, C2. Here you see that we start with like standard capacitor, 0.1 microfarad capacitor. It's available. Okay, we start with choosing this capacitor, and then how to come up with other capacitors. And then we have this R. And K1, K2, we have this. And finally, your DC gain H naught is going to be K1 times K2. Choose R1 10K, which is the standard, and RF 10K, and based on this RF, you know what is R4. R4 equals R14. So this is your R14, which is 10K, and RF 10K, and because we know RF, we can find what is R3. R3 equals K1 times 1 times RF, which is K1 is 1.152, and then minus 1 RF. RF is 10K and 1.52 kilo. And R13, you can find it like that. Using the same equation, finally you get all the values. So we found all the resistance values and all the capacitance values. And these values will make that active low pass filter with cut-off frequency 100 Hz, which means that this filter, this active filter, will be able to pass all the signals of frequency less than 100 Hz, and this cut-off frequency, this active low pass filter will be able to actually get rid of all the signals of frequency more than 100 Hz. Okay, clear, guys? So I know that I will not have enough time to write all of this. So I typed it. You will have full solution in my slide, and that concludes my today's lecture. And that concludes chapter 2 as well. Okay, so we are done with chapter. Any question, guys? Yes.
In the last three sections that just went over, like you didn't ask differentiators, whatever was before this, and then active filters, which you just covered.
Yes, because active filters, these are there are nothing new, because we went through this.
But active filters are your own slides, and there are no exercises in the book.
Yeah, no. Active filters, there are no exercise, just whatever you have on slide. Okay? And differentiator, flow rate, and differentiator. Differentiator, yeah, often differentiator, I did not like them because they follow exactly similar procedure as an integrator. Okay, it is just the opposite. Okay, so that's why I did not write down here. But you do need to go through this. You do need to be there. Clear? Any other question? No? All right, guys. So I will have office hour tomorrow.